In this lecture, I'm going to introduce the beam element. Let's talk about finite element modeling of large systems. For example, this Verrazzano narrow bridge. This is the bridge. It is a monumental structure. The towers are 211 meters high. The distance between the towers is around 1.3 kilometers. And the distance between the top of the towers is 4 centimeters higher than the distance between the base of the towers. This is just to compensate the Earth's curvature. So the question is, it is possible to model this structure using strand 7 or finite element modeling? Let's see. So the span, 1.3 kilometers. The clearance from water is 69.5 kilometers, and each tower weighs 27,000 tons. This is a huge structure. But finite element modeling can model large systems without problem. But the problem, another problem appear here is with the number of elements in this tower. This tower has 3 million rivets around and 1 million bolts. So, are we going to model individual rivets and bolts in the finite element analysis? This is the question. The other questions are the effects of the temperature in this huge structure. The seasonal contractions and expansions of the steel cables cause double decks to change from winter to summer, and the difference is 3.6 meters. So the deck is 3.6 meters lower in summer than in winter. So a finite element analysis needs to consider the thermal effects. In the finite element analysis of any particular situations of this structure, you need to consider two things: model complexity and time complexity. Model complexity is related with the size of your model, the number of finite elements that you are going to use to model the structure. And the time complexity is related with the time spent by your computer solving the finite element equations of this structure. So you have to find a balance between model complexity and time complexity. Okay, let's look at the detail of the structure. So it has many elements. I'm talking about the structural elements. Some of these elements will be simplified by finite elements. For example, this flexural member is going to be replaced by a beam element, an element with two nodes. And this element is going to have an element stiffness matrix. So here I'm showing the element matrix equations. So this is the degrees of freedom of this element, assuming 2D deformations. And this is the nodal loss in the elements. And the stiffness matrix, the element stiffness matrix, will depend on the Young modulus of the material, the area, or the cross-section area of the member, the length, nothing else. So this is for 2D. For 3D, you are going to have a similar matrix. So in this case, you have, for each node, you are going to have 2 degrees of freedom, 3 degrees of freedom in 2D. So these 2 degrees are the displacement of the nodes, and this is related with the rotations of the cross-section area at the nodes. In 3D, you are going to have, for each node, you are going to have 6 degrees of freedom, and the matrix is going to be 12 by 12. Before I forget, I need to include another variable here in this stiffness matrix, that is I. That is the moment of inertia of the cross-section area. Okay, let's see how can we model this structure using the Strand 7 finite element software. So Strand 7 is equipped with different elements, finite elements. They are classified as follows. So you have the beam 2 element that represent mostly trusses and frames. It's used for trusses and frames. So this element has two nodes. This is the linear element. It's called linear element because it's just one-dimensional. We have also two-dimensional elements in Strand 7. This is the plate, the 3-3 plate. It's a two-dimensional element and it has three nodes. So you have three nodes and the displacement inside of the plate is calculated by linear interpolations because there's the interpolations between these three nodes. So the displacement is a linear interpolations, that is a linear functions. The strain is the derivatives of the displacement is going to be constant in these elements, and in consequence the stress is going to be also constant in this element. That is why this is called the constant stress element. Next we have this element, that is the 3-6 element, that is represented shells. This is like a triangle, but the sides of these triangles are curved. They are curved like a polynomial. So this element have 6 nodes. 1, 2, 3, 4, 5, 6 nodes. So each side have 3 nodes. So the side is the interpolations, the parabolic interpolations between these 3 nodes, and the displacement is also a parabolic interpolations between the nodes. The next element is the quad 4. That is also represent plates like 3-3. So quad 4 have 4 nodes. And we have also the quad 8, it's like the 3-6, it represents shells, and it has 8 nodes. Every side have 3 nodes, and they are interpolated by parabolic functions. In these two elements, the stress is not necessarily constant along the elements. Here the interpolation is quadratic interpolations, and here the interpolations is above quadratic, it's cubic interpolations. So the displacement is a cubic interpolations, so the stress is going to change. The stress is taken from the derivative of the displacement, is going to change on the elements. So they are non-constant stress elements, like this one too. So this is the two-dimensional elements, and then we have the brick, like this one, X8 bricks. It has 8 nodes, and it covers a 3-dimensional space, and it is used to solve the 3-dimensional continuum equations. In structural mechanics, you can model the structure using one-dimensional beams and two-dimensional plates and shells. This element is not really necessary in structural mechanics, and you have to avoid this. In Strand 7, this element has a high time complexity, so you need to spend much more time solving a finite element problem with bricks. In soil mechanics, the soil is three-dimensional, and in most of the cases you need to use bricks. But if you really want to solve a problem in soil mechanics, you may try to use Plaxis that is more specialized in soil mechanics, in foundations. Or you can use Abaqus, that is a multi-purpose software, and it has a higher accuracy. Okay, in this lecture, as I say, we are going to focus in the beam 2 element, linear element or one-dimensional element. So in its most general form, the beam element can carry axial forces, shear forces, bending moments, and torques. In addition to the conventional beam elements, there are other special formulations of this element in strand 7. These are the spring damper element. The spring can have axial, lateral, and torsional stiffness, and it has a dashpot that produces damping that is sometimes used in dynamic analysis. For example, in the investigation of the dynamic response of a structure due to earthquakes, pedestrian modeling, wind loads, you need to damp the structure, and then you need to use dampers. The cable, a very common structure in bridges. The cable elements formulations solve the nonlinear equations of the catenary. These solutions in strand 7 is given only for the static analysis. So if you solve the dynamic problem, you should not use cables because the cables are only available for static analysis. You have the truss. The truss can carry only axial forces, and the strand 7 formulations allow you to model both statics and dynamics problems. And the traditional beams, the beam elements can carry axial forces, shear forces, bending, and torsional moments. These formulations work in strand 7 for both statics and dynamics. And in strand 7, you have the Euler-Bernoulli beam, and you also have the Timoshenko beam. Now I am going to go to an overview on how to construct these finite elements. So let's recap the one-dimensional bar element. So this element is the simplest element. It has two nodes. Each node has a single degree of freedom. It can displace only along the direction of the element. The element can carry a force along the direction of the element. Rho is the density of the element, and G is the gravity. So the element will have two nodal stresses, two nodal forces, P1 and P2. And the length of the element is L. So this is the element stiffness matrix for this element. So here we have the shape functions, linear shape functions, or interpolation functions. And here you have the stress at the edges of the elements, at the nodes. Here is the boundary conditions. Here is the body forces, the gravity forces, and here is the nodal displacement matrix. So to formulate these element matrix equations, you have to solve all these integrals, and you have to impose the boundary conditions, taking into account that we have here two loads applied in the nodes. So I just give the solutions. So this is the interpolation functions for this problem. So I'm going to multiply all these equations by a in both sides, and I calculate the integrals, and I am going to get these results. So it's going to be your modulus area of the element, length of the element. Here, this term account for the gravity forces, and this the applied forces at the nodes. Notice that A is not exactly the area of the element. A is the area of the cross sections of the bar. Okay, now we are going to go to the two-dimensional bar. So it's the same 1D bar. It has two nodes, but each node in this case have 2 degrees of freedom. Here X and Y, capital X and capital Y, represent the system of coordinates of the bar. It's called also local coordinate system. And small x and small y is the global coordinate system. It's a system that is shared by all elements of the structure. So in the local coordinate system, we have 2 degrees of freedom, that is u, the axial displacement, and v, the lateral displacement at the nodes. And p and q are the 2 components of the loads applied in the nodes. So this is the element matrix equations of this structure. Notice that I just add zeros in behind the degree of freedom corresponding to the displacement in the perpendicular directions of the bar. So if you multiply this by this equal to this, and this by this equal to this, you recover the equations of the one-dimensional bar. And if you multiply this row by this and equal to this, you find out the Q1 equal to 0 and Q2 equal to 0. These two equations are telling you that this bar cannot carry lateral forces. This bar can only carry axial forces. So Q1 is equal to 0 and Q2 is going to be 0. So if you want to write these element stiffness equations in the global coordinate systems, you have to use these transformations. Theta is the orientations of the element, and this rotation matrix allows you to transform the loads in the local coordinate system into the load in the global coordinate system. So if you do the mathematics for capital P and capital Q and capital U and capital V, the loads and the displacement, this is the final result that probably you are familiar with these results. This is the element stiffness matrix. This is the element stiffness matrix in the global coordinate system. And this is the element stiffness matrix in the local coordinate system. Here we simplify. C means cosine of theta and S is sine of theta. Now I'm going to introduce the beam element. So this is the element. It has 2 nodes, and each node have 2 degrees of freedom. This is the classical Euler-Bernoulli beam. So the 2 degrees of freedom are the deflections and the rotations. The rotation of the cross-section area of the beam. The actions in the elements in the nodes are the shear forces and the moment. The element has a length L, and a cross sections A, and a moment of inertia I. So here is the local coordinate system of the element. The finite element solution for this problem is performed by first expressing the displacement field in terms of cubic interpolating polynomials. Then the calculation of the deflections assume a uniform distributed load that is called W, and the details of the derivations is presented in the sections 9.2 of the lecture notes. So here I present the final solution. This is the element stiffness matrix. Here is the degrees of freedom of the elements. B1 is the deflection of the first node. This is the rotations of the first node, and this is the deflections and rotation of the second nodes. Here I have the nodal loads produced by the uniform distributed loads, W. The element stiffness matrix is given in terms of the Young modulus, the moment of inertia, the length of the element, and the area of the cross-section of the element. Now we can combine the bar element with the beam element to get the two-dimensional flexural member. So this element has more degrees of freedom than the previous two elements because it's a combination of both. So you have axial displacement, you have deflections, and you have rotations in each nodes. And the actions are axial load, lateral load or shear force, and you have moment. So this is expressed in the element coordinate system, which is different to the global coordinate systems. So to construct these elements, we just combine both equations for bar and for beam, and the results is presented here. So notice here that each element has 3 degrees of freedom. Is axial displacement, deflections, and rotations. And this is the nodal loads and the stiffness matrix. You here can see the component of the bar, and here you can find the components of the beam. So this is the flexural members in 2 dimensions. It is going to have 6 degrees of freedom, 3 for each node. In strand 7, you have a formulations for 3 dimensions, and in each node you have 6 degrees of freedom, 3 translations and 3 rotations. The translations account for axial deformations and lateral deflections, and the 3 rotations account for 2 bending rotations and 1 torsional rotations. Okay, we are going to see how can we use these beam2 elements in structures, civil engineering structures. So I have here 2 examples. This is an Amazon warehouse. This is an example of long span structures. So the distance between here and here is around 10 meters. So it's a long span beam that you have to model with special care to avoid large deflections or collapse. One of the techniques used for these long span structures are pre-stressing or special bracing. So in the Verrazzano bridge, we can model these structures using beam2 elements only. So the cables can be modeled like beam2 cables. The towers can be, each component of these towers can be modeled like a beam. And the deck members can be modeled like beams too. So the concrete and the asphalt can be modeled as plates, but you can also model them as an extra load that is applied to the frame of the deck. For the finite element analysis, we don't include the bolts and the rivets, but you have to take into account that when you drill a hole in the member, you produce stress concentrations that you have to account for. So how are we going to model a structure like the Verrazzano Bridge in strand 7? So first of all, you need to understand the structure of this computer software. It consists of three main parts. The first part is the preprocessor that allows you to do the finite element model. In the preprocessor, you can create the element of the systems, the cables, the beams, the plates. Then you have to apply the kinematic constraints and laws in the elements. The kinematic constraints are, for example, in this case, the constraint at the base of the towers. So you impose the nodes at the base of the towers are fully fixed. And the loads can be dead loads, the gravity loads, the live load in the structure used by cars or pedestrian loads. You can include the wind loads, you can include the earthquake loads, etc. Then you have to enter the geometry of each element. If the elements are beam 2, so you have to enter the geometry of the cross sections of the beams of all the beam 2 elements. Then for each element you have to enter the material properties. If the material is steel, concrete, timber, then you have to find the material properties of these materials like Young modulus, Poisson ratio, etc. This is the preprocessor step. Then strand 7 has different solvers. A solver is a component of the software that allows you to solve the displacement in the structure. And how the solver works. So inside of the computer, the first step is going to be the calculation of the stiffness matrix of each element that you include in the model. Then the computer will assemble the element stiffness matrix to create the global stiffness matrix. And then the computer will solve the matrix equations of the problem. For static analysis, it's just inverting the matrix equations. That is going to be a big matrix. The number of rows and the number of columns of the global matrix equations correspond to the number of degrees of freedom of your model. In the post-processor, the computer is going to compute the solutions based on the nodal displacements using the interpolation functions, and it's going to calculate the derivatives, the stress and the strains. And you can plot the results in different ways as a contour plot. You can pick one element and see the displacement at the nodes of these elements and the stresses, forces acting on these elements. You can make a cross cut in the model, and you can see how the stresses or the displacements change in these cross sections. All these visualizations happens in the post-processing part of the Strand 7.